The next presentation is with Julian Hunt. Can see that you just joined us. Do you want to present, or do you want me to apply the video? How to put the video?
I can present now. I have 15 minutes.
Okay, well, I will let you present then. Thank you.
Perfect. I might not be able in the round table though.
Okay, we'll manage
Perfect.
that. Don't worry.
Hi, my name is Julian Hunt. I am from the International Institute for Applied Systems Analysis in Austria, and I'll present my work on seawater air conditioning and ammonia district cooling, a solution for warm coastal regions. This research was published in Energy, this the beginning of the year. So SWAC, everyone talks about the potential for SWAC is huge. So for only 1 meter cubic per second of seawater can provide us the same cooling capacity to 42 turbines, 136 football pitches, and a large hydropower plant. And the potential is very large, particularly in islands and some potential in continents also. I have published a paper where I show the global potential for the technology, including the length of the tunnels, the capacity of the plants, and the depth of the water at 5 degrees Celsius. There are several cities, major cities, where this can be applied: Honolulu, Havana, San Juan, Dominican Republic. I didn't put the city here, but San Pierre, Malha, Ilhéus, Puerto Escondido, Recife, Port Moresby, Puerto Gentil, Salvador, Abidjan, and San Diego. So cost competitive with conventional AC technologies. I talk about these large cities because the higher the cooling demands, the lower the cost, particularly of the offshore pipeline. So, which I would like to focus in this presentation. We need to increase the demand for cooling so that the diameter of the pipeline increases. If it doubles the diameter, the area for flow rate increases 4 times. The friction in the pipeline reduces, which might increase the flow 5 to 6 times, and you have less losses, heat losses, because of the larger the area divided, the smaller the area divided by volume rate, the lowest the energy losses. So how does the ammonia seawater air conditioning scheme works? You pump water from the deep sea. This cold water is used to condense ammonia. The condensed ammonia is pumped to the city, to the cooling demand, which vaporizes, and the vapor flows naturally to the condenser. Because the pressure is lower, you don't need a compressor. It's quite similar, simple system, and operates similarly to district heating with steam, but instead of heating is cooling, instead of steam is ammonia. You have to pressurize ammonia to condense at 5 to 18 degrees Celsius. You can have several systems operating in parallel at different temperatures. Each customer will buy the cooling services at different temperatures. So the liquid ammonia is pumped to the customer, then it's vaporized, and it comes back as gas ammonia. The pressure at 6 bars, you get the ammonia condenses at 10 degrees Celsius. At 8 bar, ammonia condenses at 18 degrees. So this would be probably the range where you would work your ammonia system. Comparing steam for district heating with ammonia for district cooling. Well, let me just put something straight, clarify something. Ammonia is used in industry, right? Ammonia is used in the industry for refrigeration to distribute cold in the industry. However, there is no publication suggesting ammonia for district cooling. No one mentioned this. It doesn't exist. So this is a new proposal. It's just apply something that works in the industry and apply it to SWAC. District cooling is very expensive. It's very inefficient. It's much easier just to have an AC that already has a high coefficient of performance because the heat goes up and it's very efficient. It works well. Ammonia district cooling just makes sense if you have a very, very cheap source of cold, which is the deep ocean. So you can combine both, and then you can supply codes, have district cooling cheaply. And why ammonia is so good? So the latent heat of vaporization is smaller than steam, which is not good. The density of the liquid is smaller than water, which doesn't make so much difference because pumping liquid is not so difficult. The gas density is significantly higher, the density, which is good. And this makes the latent heat per volume similar to steam. So ammonia, in other words, is actually similar to steam to transport heat. The main challenge is to deliver the cold because the temperature difference between the room and your ammonia is only 10 degrees. For steam, the temperature is very high and the room temperature is significantly lower, so it costs less money to heat up. But cooling has an advantage. You can cool the air and the air goes down, and then you just blow the air goes down. For heating, there's a problem is that if you heat up the air goes to the roof. So in other words, ammonia is good for cooling. Comparing freshwater SWAC, conventional SWAC with ammonia, you have benefits that is latent heat. So you can use more the delta T more efficiently to cool down the customer. Comparing freshwater SWAC with ammonia, instead of sensible heat, use latent heat. The amount of mass that you need to transport, the amount of energy that you transport per mass of ammonia is 10 times higher. So you need much less pumping capacity. Your tubes have to be significantly smaller. You can use high density polyethylene tubes, plastic tubes that sustain 6 bar pressure. That's normal. You have natural gas pipes distributing natural gas at 6 bar already operating with high density polyethylene tubes in every major city. You have temperature difference for delivering the codes much higher, which increases significantly reduces the cost of the system. Customer investment requirements is lower because the lower pipes, you require lower pumps. The capital cost is smaller. District cooling capital cost smaller also. Pumping costs smaller. District cooling distance. So this apply for long distances. For example, you can have 15 kilometers from the coast and you can still apply SWAC. Maybe even 30 kilometers away from the coast, you can apply SWAC with ammonia. With seawater, that's not possible. The risk of accident, yes, there is risk of accidents. But for example, you have a huge network of natural gas pipelines in every major city, and that already has risks. It can explode. Ammonia has an extra risk because it's toxic. Natural gas is not toxic, but you can provide you can make sure that your system is reliable, robust. If you have an accident, you close valves quickly and you restrict the impact of the accident. You have thermal energy storage with seawater tanks, so you can store energy with seawater tanks, and you also can store energy close to the customers with ammonia. You can have a tank of ammonia close to the customers to optimize your district cooling system. With water doesn't work because it would take a huge volume. So this is an example of the system. The seawater can cool down a process as ammonia system of 6 bar, and then another ammonia system of 7 bar, and then another ammonia system of 8 bar, and make as much use as possible of the sensible heat of the seawater. The seawater can then be used for other purposes, for example, vertical farming or other productive means. And then the seawater can come back very, very warm, which is convenience, of course. So this is comparing the energy storage potential of ammonia. This amount of ammonia stores the same amount of this amount of fresh seawater, seawater, and the same amount of energy that you store in 18 Tesla semis. So you can store a lot of energy close to the customer with ammonia. Why would you do that? Because you can optimize the district cooling system. When at night, for example, when the customer is not demanding a lot of cooling, you can pump the liquids to these storage reservoirs. And then when you have a lot of consumption, you can use your cooling distribution system more efficiently. And then you store the water, the ammonia close to the SWAC plants. Of course, you always have to have the same volume of liquids, because if not, the pressure inside the system will increase too much. Ammonia is toxic, of course, but you have to make sure that you make the arrangements to make it work. And another aspect, interesting aspect, is that you have billions of dollars being invested in the hydrogen economy in the next 5 to 10 years. And ammonia is part of that. So people will get used to ammonia. Ammonia will be used in more frequently. The cost of ammonia will reduce, and this will help this implementation of ammonia and SWAC. So in conclusion, you have the SWAC is a sustainable source of energy with huge potential for tropical islands and coastal regions. SWAC is a valuable alternative for 100% renewable generation islands. It's a renewable energy source of energy. For example, a 17 meters square per second seawater flow can provide up to 1 gigawatt of cooling, which is a huge amount. The higher the cooling demand, the lower the cost for cooling for SWAC, and ammonia helps that because it increases the demands that you have with the system. Ammonia district cooling is a missing link for SWAC district cooling. Ammonia is a better alternative for cooling thermal energy transport than steam. So ammonia transports heat or cold better than steam and cheaply. In the future hydrogen economy will make ammonia more accessible, and people get more used to ammonia. Thank you so much for your time. I hope you enjoyed it, and I'm available for answering your questions.
Thank you, Julian. It was very interesting. So we have a first question from Dan Iderley. Is it also feasible to use CO2 as a refrigerant linked to SWAC?
Yeah, CO2 at 1 bar pressure melts at something like minus 80 degrees Celsius. So that's too cold. And in order to freeze CO2, you need a lot of energy, and the coefficients of performance will be too low, will be 0.5. So then you spend a lot of energy and in order to liquefy the CO2, and it's going to require too much energy to liquefy CO2, and that's not going to be efficient. So the COP of the system will be 0.5%. If you use ammonia and SWAC, the COP can reach up to 30%. That's the main reason why you wouldn't use CO2. Or, for example, liquid air. You can liquefy air and transport liquid air, but the efficiency will be even lower. The COP will be 0.3, 0.2. In these cases, it makes make more sense to turn on the air conditioning.
Okay. We have a second question from Martin Brown. What diameter of cold water intake pipe optimizes the efficiency?
Yeah, I am a researcher. I don't work really too much on the field. Of course, it would depend on the cooling demand. I have to see, for example, it will be similar to, it will be small pipes. I don't know exactly how small. I'm sorry, I don't have this answer.
No problem.
I
I
didn't
can
go.
help here a little bit because this is the next part of the optimization. I already mentioned that the flow rate will influence the head loss, etc. So flow rate will influence the pipe diameter, pipe sizing, and then it
Yes.
will pipe sizing and the length, and then it will influence also the head loss, which will influence the pumping system. So actually, each location will be different, but there will be ready optimization model for it. So we have all of the formulation already ready, which will be able to put for the individual site, and it can be calculated.
Thanks so much for your answer.
Thank you, Ola.